everybody. I'm João Gabriel. I'm a master's student in the Department of Computer Science from the University of São Paulo, advised by Professor Alfredo Goldman, who is also here. And I'm going to talk about, as Kai already introduced, a little bit of what I've done in my master's research, which is the implementation of Warm Start on Globus Compute. So quick overview, I'll just briefly mention the motivation behind this work, then the core feature of my research, which is the Warm Start engine. And then I'll show a little bit of the experiment I conducted and its results. So we're mainly motivated by serverless and function as a service, which were newer technologies that were being more studied and becoming more used. And we wanted to work also with open source software, and that's how we kind of arrived in Globus Compute when it was still FunKex. And we chose the code start problem as a specific research because it was a prominent problem. We found it in lots of places and lots of tools. And talking with Kyle, even he said that this was one of the features that would be nice to have. So for this, we created a warm start engine, which is a new engine in the Globus Compute code that implements warm start for functions running without containers. I know that I've seen that there is the possibility of singularity containers with reuse and stuff like that, but we wanted to do a little bit aside from that and look at pure Python processes and workers running freely. And we did this engine based on the high throughput engine, mainly because I saw that the Globus Compute engine was mainly built on Parcel and was calling things of Parcel. And since we already had Globus Compute as a scope and we were already studying it by quite some time, we decided to use the high throughput engine, which was more everything was coded there inside Globus Compute. And we created this new engine with the idea of not messing with any of the existing code, doing all in this new engine, so there would be no risk of meddling with anything outside of it. And we developed two warm start techniques in this engine, the configuration of keep alive time and a new dispatch algorithm. So the keep alive time, the first thing we done was to change the time from 1 to 5 minutes. So managers and workers, they are there. If they don't receive anything for 1 minute, they just shut down. We increased it to 5 minutes because we saw there was a paper that Kyle sent to me, which is the Globus Compute data set. And there was a finding from the interval calls between functions. They proposed that maybe if there was 5 minutes of keep alive instead of 1, 93% of functions would not need to have cold start because everything would already be initialized. So we changed this time to match this finding. And we also allowed the user to configure the skip alive time via the creation of a new strategy, thinking specifically of even new developments with this keep alive time. So here in the warm start engine, we have the keep alive time as a parameter, and here we initiate the strategy that just uses this keep alive time, and then we ensure that the worker idle time is also matching the skip alive time, because when I was modifying the code, I saw that sometimes, depending on how I put the parameter, the managers were being shut down after 1 minute, even if I set the worker to 5 minutes, because they are not the same parameter. So I guaranteed that the value that the user configure it in the config file is propagated to both managers and workers. And so this was the keep alive part of the development. And then we did a new dispatch algorithm with the idea of executing functions on resources they were already executed. So when a function is to run, it has to load its dependencies. So the main ones, NumPy, SciPy, this torch, and this kind of thing. And if you guarantee that a function runs in a worker that already ran it previously, then the libraries are already preloaded, so you don't have to load them again. So this was the basic idea. And to achieve this, we did 3 steps. We propagated the function UID, then we created a new way to dispatch functions from managers to workers, and then from the interchange to the managers. So the propagation of the UID was a tool that we used so we could identify functions inside of both managers and workers, so we knew exactly which function the task was wanted to run. And this here is the only modification we had to do in pre-existing code. We needed to go a little bit outside of the engine because the endpoint handles the UID and then it does not use it anymore. So we needed to alter that. So in the Globus Compute Engine base, which is the class that every engine derives, we created a new method that is submixed with function ID that its implementation basically calls submit again. So all the engines would still behave exactly the same. But in the warm start engine that we created, we added this method with a new implementation that sends the function UID together with the task. So we also altered the task class to be able to handle this function UID, and then we could work with it. And then you just change the call in the endpoint interchange. Instead of using the submit method, use the submit with function UID. Any engine will still, in the end, be calling the submit method. Only the warm start engine will have this specific implementation. Now that we had the UIDs and could identify the functions, the first step was to make the manager assign functions to workers that already executed them. So I created a function worker map, mapping each function to a list of workers that already executed them. A task function map, mapping the task ID to the function UID, just so we can retrieve it easily. And a set of busy workers. The set of busy workers was created because in the Globus compute, to get a worker, you just have a first in, first out system. But now, if we want to choose a specific worker to send the task, we need to ensure that we don't send a task to a worker that already is running another one. So here we changed the code of sending tasks to workers. So instead of getting the worker with the queue, now first you look at the function worker map and you see if there is any worker that already executed that function that is available. And only if there isn't anyone is that we go to the queue again and get the next one. And after sending this, we make sure that if it was a new worker, we add it to the function worker map. So if this function comes again, we can send it to the same worker, so we don't have to load the libraries again. However, this is not sufficient because if the manager sends to the right worker, but the interchange does not send to the right manager, it won't work. So we did basically the same idea. So we created a function manager map that maps each function to a list of managers that already executed that task. And we needed to redesign the dispatch algorithm. The dispatch algorithm originally iterated over the managers. And then while these two had capacity, they got a new task and sent it to them. Now, since I need to know which manager to send a task, I iterate over the tasks, seeing if while there's still available capacity in the managers, and then assign it. So here's the dispatch algorithm I created. I can increase it a little bit. So here I get the total free capacity of the system. So I add up the capacity of all managers. And if there's still capacity in some of them, we get the next task. We look at its mapping and you see if there is a manager that is listed there with capacity and we send it to them. If there isn't, the same behavior as originally, just get a new manager with available capacity and that's it. And here's just to show how we calculate the capacity, is the same calculation that was already being done. We just add all managers to see that we still have some place where we can send the task, or else we just finish the processing and leave the task to be assigned later. Then we tested everything, made sure it was working, that this rerouting was okay, but we needed to test if there was really any kind of improvement. So we did some experimentation. I I talked to Kyle and he suggested the TAPS benchmark. So we chose two of the benchmarks in TAPS, the molecular design and Chilex factorization. And the experiment was basically running both simultaneously. We tested it in 3 versions, the original Globus compute version. I used this specific commit because it's the one that I use it to fork the repository and start my work. The keep alive version, which just has the 5 minutes of keep alive without these new dispatch techniques, and the warm start version with all the modifications. We did this intermediate version too, both to check if the finding of the paper was good, so if the increasing the keep alive would actually help, and also to guarantee that if the warm start had improvements, we wanted to guarantee that they were because of the new dispatch techniques and not only because of the 5 minutes. So we needed to have these two measurements. And then we ran the experiment on an EC2 instance with the Globus compute endpoint with 2 managers and 2 workers each. And it had 4 CPUs and 16 gigs of memory. So we collected 27 runs of the experiment for each one of the versions, only 25 for the original, mainly because of the time constraints. And for each function, so you get one execution of the experiment, and for each function, I calculated the average time of execution, assignment, and things like that. And then we use the man-Whitney test because it's good for comparing average of averages. And since we don't have a lot of experiments because of time, it's good to use. It's a good test to use. And we analyze 4 intervals of time: the execution time of the function, the assignment time to see if there was any overhead in the new dispatch technique, the total task time, and the full experiment time. So in the execution time, what we found is that for all functions, the warm start version outperformed the other two, and keep alive outperformed the original, with the exception of the run model. So here we have an example for the TRSM function from the selective factorization benchmark. And we can see that in the original version, it takes some time. The keep alive, it takes lower times, and the warm start even lower. Then we also looked at the assignment time, as I said, mainly to check if there was any overhead. And we detected 4 different behaviors. So for 2 functions, there were no difference between any of the versions. So we can see here. And here is worth mentioning that this is the only measurement of the whole experiment, the whole intervals of time that we measured, where the average of the keep alive version was smaller than the average of the warm start version. We had also 2 functions where there was no difference between the warm start and the keep alive, but they were better than the original. 3 cases where the warm start was better than the keep alive, and then this one was better than the original. And we had one curious case where there's no difference in original and keep alive, and no difference between keep alive and warm start, but there was difference in the warm start and the original versions. And when I say had difference, I mean that the man-Whitney test detected that we can, with 95% of confidence, to attest that the warm start will generate smaller times than the original version. Then for total task time, which is the moment the task arrives by the cloud service until the moment its result is sent back. And we had behaviors similar to the assignment time. So not to repeat myself, I just here a quick example. So here we have a version where we also have the warm start better than the keep alive, better than the original, and one where keep alive and warm start had no differences, but they were a little bit better than the original version. And finally, we look at the full experiment time because we wanted to see not only functions, but the workflow, if the workflow completed would have a significant impact of time. And here we can see, and the test detected, that the warm start version was a lot better. We can see that the times are mainly focused here in 1000 seconds with a few outliers. The keep alive version has a lot of variance, but it still ended a little bit better than the original, which was mainly concentrated in about 1 hour for each run of the experiment. And we see that there are no outliers. So the original function never is fast, like 15, 20 minutes, while warm start is mainly around this time. And basically that's it. If you have any questions, I'm free to answer them, any suggestions. Thank you very much.